Hello everyone, welcome back to the channel, and today we're going to talk about insertion sort. To start off, I want to tell you the one sentence summary that I have thought of. So for insertion sort, it may be thought of as, well, inserting the element into the correct position. But I think that may be a little bit confusing, and it may make people confuse insertion sort with shell sort. So let's do it this way. Switching the positions of elements until that particular element is at the correct place. Let's do that with an example. So I have an array here, and underneath I have the indexes. So the idea that the array can be split into the unsorted part and the sorted part is helpful in this situation. So now the whole array is unsorted, so the right hand side would be unsorted and the left hand side would be sorted. Now nothing is sorted. We start with the first element. So there's nothing on the left hand side to insert it in, so we will think of it as already sorted. Next, we go to 1. Now, the idea is to switch the elements until it's in the correct place in the sorted subarray. So 1 and 5. Is 1 smaller than 5? Yes, so we swap them. There's nothing else to swap with, so we stop there. We go to the next element. Is it at its correct position? It is in the sorted subarray. It is in the correct position, because we know that all elements ahead of it's the part of the sorted subarray, so we don't really care about the sorted part at all. So to mark it, I think I will just color it to keep track of which element we're talking about. Notice that all the color elements are in its correct position in the sorted subarray, not in its final correct position. We only have 2 elements left. So for 4, is 4 smaller than 9? Yes, so we swap them. And then is 4 smaller than 5? Yes, we swap them. And then is 4 smaller than 1? No. So we know that it is at its correct position. Again, correct position in the sorted subarray. We're now at the last element, and now we can eyeball it. We will need to do a bit of work here. So 0 smaller, swap. Notice that I don't really do like, oh, I know, because I can eyeball it. I know 0 must be the first element, and I'm just like, whoops, and then push every element to the right. That's not how insertion sort works. The element itself is compared to each element in the sorted subarray. So 0, 5, smaller, swap. Of course, smaller, swap, and then smaller, swap. And then we know that it has been sorted because we have just walked through all elements in the array. Yep, that is how insertion sort works. We will now write the code for it, and I would recommend pausing the video a little bit and write your own version of insertion sort. Think a little bit also about big O analysis, time complexity, space complexity, stability, and whether it's in plex or not. Now let's walk through the code together. This is our code right here. Notice that we have 2 for loops. The first for loop is to be used to iterate through all the elements in the array. The second for loop is to iterate through the sorted subarray and to insert the current element into its correct position in the sorted subarray. So As you can see, we start from I because we want to start from the current element that we're interested in. And then if it's smaller than the next element to the left, we switch the position. And we keep switching until we have nothing left to switch with. If it's already bigger than the next element to the left, we know that all elements to the left of the current element is already sorted. So if it's bigger than the next one, then it's already bigger than the biggest in the sorted subarray. So it must be in the correct position in this sorted subarray. That's why we break from the for loop at this point when the if statement is not satisfied. And then we continue until we run through every element in the array. Right. Just a quick note that please don't write your comments like this when you actually write this in a coding environment. Because I like space and I'm writing this on paper, I'm writing comments on multiple lines. So I would recommend against doing this in your coding. Now for analysis, insertion sort is stable because of the, as you can see, because of the comparison right here. It's also in place, that is almost no additional memory is required. The time complexity, the worst time complexity would be O(n) squared. As you can see, we have two for loops, and then for each element we go to the all the elements in the sorted subarray. So it's technically a little bit a little bit less than 1 times n squared, maybe n squared times a constant, but as you know, big O analysis means getting rid of the constant, so we just focus on the fact that it's quadratic. It's also quadratic in an average case. For the best case, when the array is already sorted, that is when we're given this array, for example, we will make about n-1 comparison. So this is where the comparison happens. So n-1 of this, and then 0 exchanges. So these are the exchanges because it's already already bigger. Then we don't really swap anything when we break out of the for loop. So that is it. That is insertion sort. If you have any questions, feel free to leave them in the comment section. We will talk about merge sort next time. So thank you for watching and see you soon.